designate each group with the particular topic that you will be presenting. So, pag sinabi po natin na mag-present, you can have po yung PowerPoint presentation or po yung videos or any other activity that you want to do for to maximize learning po with your classmates, right? So, if you will be using po yung PowerPoint, make sure it is not yung copy-paste. Eh. Halimbawa po, kinuha natin from a reference, yung paragraph form, pinis na lang basta doon sa PowerPoint natin. So, hindi naman po ganun yung gagawin, okay? So, it should be in bulleted form. So, phrases lang po. And if you are presenting, huwag din po natin babasahin yung report po natin. Ang gagawin po natin is simply to discuss the phrase or the bullets na nilagay po natin. The simple, the better po. Okay? Yung kung may paliwanag niyo po on your own interpretation, mas maganda po. Okay? Yung para po mas madaling maintindihan ng pong nakikinig sa atin. Okay? So, we'll have here po the wheels of names po to determine the topic na maa-assign po sa ating pen group. I know naman po, we have our groupings already. Tama ba, Janela? Are they aware of their group numbers?
I'm 26.
Yes.
Okay, so later po, tatawagin ko po per group. Okay, so to see kung sino yung mga members ng kada group po natin. Okay, so for each group, please assign a leader for your group para po siya yung magbahagi ng mga topics, okay, doon sa bawat po members. So everyone must have their part po. Okay, you will be graded accordingly sa activity po.
So ang ating point
Okay?
ay negative 1 ng x at 26 ang point.
I think that would be by next week po, okay? So, kung hindi man po next week, it would be the week after next, okay? Kasi parang next week po is the holiday. So, madami pong holiday. So, ilan lang po yung meeting natin. So, you must prepare for it po, okay? For your presentation.
Minimum and absolute.
Okay? So, what are those topics po or materials that are to be present? Okay? Una po is, of course, yung metals. And then you have ceramics, polymers, composites, and then we'll add po biomaterials. And the last one would be nano and smart materials. Okay? So, yun po yung magiging groupings po natin. So, ano po yung mga i-discuss natin with regards to this particular material? So, again, we will be following po the components of your materials engineering. So, what are those components? So, we have there the structure, the properties, the processes, and the applications. Okay? So, we focus on this po. Okay? Yung pong discussion natin, nakafocus po dun sa apat po na iyon. Okay? So, bahala na lang po yung atin pong leader kung paano po niya babahaginin. Now, there are those modules na natapos na po natin which may be the same doon sa specific na material na naka-assign po sa inyo. Halimbawa po sa metals. Okay? So, there are those modules, specifically, halimbawa po yung atin na crystal structure, which defines the structure of the material. Okay? So, maari po sa ating discussion, okay, pwede po nating sabihin lang ng kaunti, pero hindi na po natin uulitin pa yung nagdaanan na module. Okay? So, yun po ang ibig sabihin. So, we focus more now on kung alin yung hindi pa natin natakil. Okay? So, pwedeng daanan nyo lang saglit, okay? Review lang ng kaunti doon sa dating module kung siya po ay kumbaga ay relevant doon sa yung dinidiscuss, pero wag na po natin uulitin. Okay? Wag na po ulitin na as in yung buong halos yung module na yun, yun din yung discussion. Okay? So, hindi na po iyon. Maliwanag po ba tayo? Naintindihan po ba yung assignment natin?
Yes po, ma'am.
Okay, good. So, I'll be showing to you now, okay, yung pong atin na wheel of names para po sa atin na specific na topic na pa-assign per group.
Paano naman
Okay.
yung nakuha rin x equals 0?
Lang po ha.
Ano naman ang ginamit nila? Ano ba ang magpapa-undefined na rin? Na rin 2 over x to the 1/3. Anong x ang magpapa-undefined?
So, kindly, ano po yung ating group 1, okay? You raise your hand po, group 1.
Dalawa pa rin ang critical point. 0 yung isa para sa undefined.
I see here around 6. Sino pa po?
1 naman sa ang overall.
Sino pa po ang kasama dito sa group 1? So, we have here Michelle,
Are these
Althea,
part of the interval?
Micaela, Pin, Cherry po, and
nasa
Rick.
loob ba siya ng negative 1
Okay, so we have here 6. So, as I know po, yung pong ating per group is around 7 to 8. So, sino pa po kaya ang wala?
So, pwede
Okay,
sila.
so ito lang po ang 6.
At dahil dalawang critical.
Okay, so sa atin po, okay, kung hindi po tumutuloy yung isang ka-group or wala po, okay, so pwede pong paghalahan na lang ng kung sino po yung present, okay? So kung wala pong presentation, then he or she will be marked 0 for this particular activity, okay? So, halimbawa po absent during the presentation, so any of the group members may cover po yung kanyang topic, and then he or she po would be graded accordingly na 0 po. Okay? Kasi hindi po siya nag-present. Okay? So, yun lang po ang ibig ko sabihin. So, we have here 6 for group 1. So, let us see what would be the topic na ma-assign po sa inyo. Yan, okay. So, you are the metal group. Okay, yun po yung group 1. Okay, so sabi ko nga po, meron na tayong module na nag-define minsan yung properties, yung structure ng metal. So, i-ano lang po natin, ihapyaw lang po natin ang pag-discuss, and we focus more doon sa mga hindi pa po na tackle po. Naintindihan po ba, group 1?
Naiintindihan po.
Okay, good. So, you choose a leader for your group para po merong sa atin, mag-lead po sa atin as to the division of the topics for metals. Okay? So, you lower your hand na lang po. Okay? Okay, group 2 naman po. So, 6 for group 1.
Next. Among the 4 values, which is the highest, and that will be the maximum.
Okay, there are also 6 for group 2. 7 na po. Wala na. Okay, so there are 7. Keisha, John, Justin, Ray, Romelia, Justin, and Adrian. Okay? May isa pang pakuli-huli. Last year, Joseph. Okay, so you are 8 in the group. Okay, so here's the topic for you.
Although similar sila doon sa open interval kanina, hindi interval ang basa nila.
Okay, so you'll work on polymers. Okay, so polymers, that includes the plastics and the rubber. Okay, and any other types of polymers. Okay. By this time, group 3. Paalis muna po yung group 2. Okay, group 3.
Ang ginawang proseso.
5 lang ang nandito po na group 3. Wala na po. Nasan po yung iba? Baka tulog pa.
Find the absolute extrema of the function sine squared x plus.
Okay, so we have here 7 for group 3. Janela, Renzo, Leona, John, Zigel, Nino, and Japet. Okay, so we have 7
So,
for
hindi lang
group
yan
3.
habang algebra ha, kasama rin ang mga transcendental. So, step number 1, find the critical
Okay,
value.
so for you, it's
get the first
discussion would be on biomaterials. Okay,
The
so
first
ano-ano
is
ba
a
yung
power
mga
rule, that is
samples
sin
to
x
biomaterials natin
So,
na
may inner
sinasabi
function
and
na
what are
sin
its
x,
common
ang outer ay
applications.
power
Okay,
of 2.
group 3.
So, to get
Group
the
4.
derivative of a power, so bring down the 2.
Lower your hand, group 3.
Copy the inside function sin x, then derivative of sin x. So, u, 2,
Group
u,
4.
du. Ano? O, derivative
Ito,
ng
group
sin
4 na
is
ba
ay
ito?
cosine.
Japet,
Ayan.
Almac,
Plus,
Reniel,
the
Jonel,
second term,
Daniel,
the
Joseph.
derivative of cosine is
Lahat po ba ito ay
negative
group
sine.
4 na? O ito yung kanina pa?
So, ito ang ating first
Okay,
derivative.
group 4.
Tanda pa ba yan?
Others.
Dami sa inyong
O, 5 lang.
Ligwak eh.
Hello?
Nakalimutan na agad. Ano?
Ari lang po yung group 4.
So, di dahil tapos na yung midterm ha, ay hindi po
Okay,
ibig
so
sabihin,
group
kakalimutan
4, 5 lang po. Meron tayo. Si Almac, si Reniel, Jonel, si Daniel Joseph, at si Christian
wala
Carl.
namang magpapa-undefined dito.
So, kindly,
So, ang
ano po,
ating lang gagamitin
pakilagay nyo
dito
po
ay
yung
ang
pangalan ng mga
magpapasibo
kagrupo nyo. Okay? And then we have here
So, what
5
will make this
for
zero?
group 4.
So, first, we do factoring. O anong common factor sa first at second term?
Okay, you work on
So,
decomposites.
beans are
Okay, so
sin x, correct.
you cite several samples of
And you will get
composites.
sa
and their
first term,
uses.
2 cosine x
So,
minus
marami po
1
tayo
sa
mga
second.
composites.
Then,
Okay?
ito ang equal
And then,
natin sa
tingnan
zero.
natin
So,
alin
dalawa
yung
ito.
pinaka-common
Ang isa,
po natin
yung
na
sin x
ginagamit.
equals
Okay?
0. Ang pangalawa, ang 2 cosine x minus 1
Fifth
equals
group.
0. Sa pangalawa, cosine x, i-transpose ang 1, i-divide ng 2 is 1 half. Ayan. So, alamin natin ha. Sa
So, ayan. So, madami aring group 5. Okay, very good. So, we have Aldrich, Aliana, Aliyah, Ken, Prince, Tristan, Robert, and Nino. Okay, Nino Rafael.
Kasama ang nasa first, second, third, and
Sino
fourth
hindi kasama
quadrant.
din eh? Yung si Nino Rafael.
Okay, ano ang value na magbibigay sa first quadrant ng
Okay, so
sin
we
x
have here
equals 0?
7. Again,
Anong ang
we have Robert, Tristan, Prince, Ken, Aliyah, Aliana, and Aldrich. Okay, so again, you select from your group sino yung pwede maging leader to assign topics on this material.
Vince Arthur, first quadrant muna tayo. Lumali ka na naman, nagbasta ka na lang.
Yan, okay, so for you, it would be both nanomaterials and smart materials. Okay? So, ito pong dalawang ito, pinagsama na po natin. Okay? Since maliit na area lang naman po ito. Okay? So, smart at saka nanomaterials. Okay? So, magkaibang discussion po yun. Again, pinagsama lang po natin since as compared to other groups, kakaunti naman po ito. Okay? So, and of course, the last group will work on the ceramics. Group 6. Who are those group 6?
Oh, di ba?
Oh, ito, Lilima din, ang group 6.
Oh, Vince Arlo,
Hello. Nasaan pa po yung iba, group 6 natin? So, we only have here Kyla, John Carlos, Thea, John Peter, and Kurt.
Anong sagot?
Where are the others?
Oh,
Ana?
may 180 kanina. Saan mo kayo na ngayon?
40, ano naman tayo, kompleto naman tayo dito. Bakit po ang iba ay hindi nataas yung kamay? So, ibig sabihin po, naka-open lang po yung ating mga account, pero you are not around kasi tinatawag na ay wala pang
So, you
nasagot.
need to be
Okay?
first
So,
listen to
tandaan
what
lang
is
nyo po
given
ito.
instruction.
Okay? Yung 5 lang po itong nasa atin
So,
na
ulit, Miss Arthur,
group
what is
6.
your answer
Okay?
to that?
So, ano po yung para sa
Sin
group
x
6?
equals 0
You
in the
work
first
on
quadrant.
the ceramic materials.
Okay,
Okay?
0. Okay.
Maliwanag
How about
po
in
ba?
the second quadrant? O, ikaw na rin. Ang sunod ko.
Hello?
180 or
Yes po,
5.
ma'am.
In the
Okay,
third
good.
quadrant.
Okay, so pakitandaan lang po sino yung nandito lahat. Okay?
Pauli.
Okay, so may question po tayo regarding the presentation.
Di ba, part ng third quadrant ko rin yun, di ba?
Wala naman po.
Diba? O, in the
Okay.
fourth quadrant.
You lower na po
Oh,
your
2,
hand.
5.
Okay, yun
So,
po.
therefore, tatlong
Yan.
rugin.
So, kung wala na po tayong question dito, okay, so I will be giving you din naman po yung time para makapag-conduct or makapaggawa ng inyong presentation. Okay. So, this week po, we are having po our experiment. Okay, so I have talked already to Janela nung pong ating exam, okay, and I asked for your free time, okay, para po makapag face to face dito. Okay, so doon po sa original po natin na schedule, okay, sa original po natin na schedule, ang atin pong schedule ng laboratory is Wednesday 3 to 6 p.m. Okay? Wednesday 3 to 6 p.m. Okay? And then sabi ko nga po, ngayon pong week na ito ay tayo po ay hindi face-to-face, online po tayo. Okay? But then, since napasked po yung ating experiment this week, so I am asking your utmost cooperation po to come to school, okay, on our scheduled laboratory. Okay? So, para po, yung pong meeting po natin ng laboratory na tomorrow, okay, it will be replaced po nun pong ating gagamitin sa face-to-face this week. Okay? So, in-schedule ko naman po iyon doon po sa inyo na free time. Okay? So, it would be on Thursday po. Okay? It would be on Thursday. It would be on Thursday for section 3105. It is on Thursday 8 to 12 noon. Okay? 8 a.m. to 12 noon. Okay? Nasundan po ba? Hello? Nasundan po? Napapakinig pa po ba?
Yes.
Okay. So, bukas po, yun pong ating online class na 3 hours.
8 to 12 po.
Hello? Yung pong online class po natin tomorrow na 3 to 6, okay, na laboratory, ipapalit po natin doon yung face-to-face po natin kasi tayo po ay mag-experiment sa Thursday. Again, Thursday po, 8 to 12 noon. Okay? So, we will be conducting po yung tension test po natin. Okay? So, tension test po, doon po sa STIR Hub, Material Testing and Calibration Center. Okay? So, pag-conduct po natin ng experiment, okay? So, per group lang po ang papasok po doon sa center. Okay? At yung iba po ay doon muna po sa labas. Okay? So, hindi din po doon tayo mag-stay sa STIR Hub, kundi doon muna po tayo sa may parking area ng STIR Hub. Meron po doong mga bench, okay? Doon po tayo muna mag-stay. Okay? So, para din po hindi marami yung nakatambay, okay, at nag-iintay, okay? So, gagawin po natin schedule, okay? Groups 1 to 3, okay? Groups 1 to 3, yun po ay papasok ng 8 to 10. Okay, so dun po tayo 8 to 10. Tapos po yung groups 4 hanggang 6, okay, 4 to 6, 10 o'clock na lang po kayo pumasok. Okay, so kayo po yung 10 hanggang 12. Okay, para po hindi tayo masyadong marami doon. Nakukuha po ba? Naiintindihan po ba?
pangalawang sinabi ko.
Yes po, ma'am.
Okay? And ano po yung dadalhin natin? Ano po yung specimen na gagamitin natin for the experiment? So, kayo po yung magpo-provide noon. So, ano po ang ating gagamitin? Okay? So, you will bring po steel rebars. Okay? Steel reinforcement bar po iyon. Okay? So, yung steel reinforcement bar po, okay, yan po ay circular yung cross-section. Tapos po, iba-iba pong sizes yung gagamitin natin. So, tatlo pong sizes yung gagamitin natin, tatlong diameters. Okay? So, yung una po would be 10 mm. Okay? 10 mm diameter. Ang pangalawa po is 12 millimeter diameter. At ang pangatlo po ay 16 millimeter diameter. Okay? So, tatlo pong specimen ang daladala per group. Again, per group po iyon. Okay? Ano po yung length ng tatlong yon? Lahat po yon, ang length ay 460 mm. 460 millimeters. Again, length is 460 mm. Ang diameters would be 10, 12, and 16. Okay? So, ang magiging testing po natin, ang i-vary lang po natin is the diameter. Okay? Length will be fixed. Same thing with the type of material. Okay? Lahat po ay yung steel rebar ang gagamitin natin or steel reinforcement bar. So, I suggest Miss Janela, okay? So, pakiano na lang natin, pakilid na lang yung buong klase, okay? Para yung sa pagbili, sayang din naman kasi pag binibili po iyon, isang mahaba kaagad na bakal. Okay? So, puputol-putulin na po. Pag puputol-putulin na po ng 460 mm na length. Okay? So, you may coordinate also with other sections, okay? With other coordinators para pagbili ninyo ay ma-maximize nyo yung yung isang buong material, okay? Para hindi rin po masyadong malaki yung magiging gastos. Kakaintindihan po ba, Miss Janela? Okay. And it is also advisable that you provide yung spare. Okay? Hindi naman ganun kadami. I am not saying naman na all groups ay may spare tayong ilalagay. Just in case lang po for the full class, may nag-fail na na test, di meron po tayong ipapalit kung sakali. Okay? So, yun po. So, normally po yung pinakamalaki, yun po kasi yung medyo mahirap putulin, kaya minsan nagkakaroon ng slippage po doon. Okay? Or nagbe-bend lang. So, normally, doon po nagkakaroon ng error. Pero doon naman po sa maliliit, usually ay maganda naman po silang i-test. Okay? And then another thing is, aside from this test specimen, ano po yung gagamitin natin na tools, okay? So, you bring also caliper, okay? So, yung caliper po gagamitin natin to measure the diameter of the specimen, okay? Before and after the test, okay? So, yun pong caliper. And then, ang isa pa po is yung pong metro. Okay? So, magdala po naman tayo ng metro para naman po doon sa pag-measure ng length ng ating test specimen. Okay? So, yun po yung mga dadalhin. Okay? So, wag na pong pupunta din kung wala po tayong dala noon. Kasi, yun po yung mga gagamitin natin. Wala po tayong magagamit dito kung wala po kayong dadalhing test specimen. Okay? Yan, per group po iyon, per group. Okay? Pagkakatapos lang po ng isang group, tsaka po susunod doon sa center yung pangalawang group. Okay? And to assist po sa ating pag-experiment, okay? So, kasama po natin ang ating laboratory technician, si Sir Andrew. Okay? So, at first, ituturo po sa atin ni Sir Andrew kung paano yun i-operate. Okay? And then, sa sunod po, edi yun na pong group members, o kayo na po yung titest po ng ating mga specimen po na iyon. Okay? So, iingatan lang din po pag nagte-testing po kasi we will be liable po doon sa equipment. Okay? Once na meron po doong masira. Okay? Ganon din naman po. Okay? So, you behave properly and ano po natin yung safety ng bawat isa. So, wala po tayong maglalaro doon sa laboratory at lahat po ay nag-experiment lamang. Okay? So, lahat po ay makikinig at gagawa. Okay? So, another thing po, another reminder po, okay? You wear po closed shoes. Okay? So, closed shoes po yung gagamitin and you bring po goggles. Okay? For protection po ng ating mata. Okay? So, kasi po baka mamaya tumalsik yung test specimen pag naputol. So, maganda na po yung meron po tayong gear para po maprotektahan po tayo. Okay? So, kanya-kanya po yun nadala. Okay? So, make sure po meron po kayong dala. Otherwise, hindi ko po kayo papapasukin doon sa center. Okay? And make yourself available po bukas sa experiment po natin. Okay? Kasi you will be marked 0 po kung hindi po tayo makaka-attend noong atin na experiment. Okay? Another thing po is aside from this experiment, you are to submit also a group report, okay? Stating the observations and the results of your experiment. So I'll be giving you naman po the template of this experiment kung paano po natin gagawin. So ang mahalaga lang po is you take down notes, okay? You take down the data during our test. Okay? So yung pong specific na mga data na need po natin, I will be discussing it po once we have our laboratory na po. Okay?
Dalawa. Pwedeng dalawa.
Okay, maliwanag po ba? Groups 1 to 3, yun po yung 8 to 10. Okay, and then 10 to 12 will be groups 4 to 6. Okay, groups 4 to 6. So, bibilisan din po natin gaano yung pong pagtitest para po everybody ay makatapos po on time.
Naintindihan na po.
Okay.
Yun ang gamit ng calculus.
So, yun po yung para dun sa laboratory natin on Thursday. Okay? And then, I'll be showing to you now po yung mga videos. Okay? Videos po of the different mechanical tests. Okay? So, here, yung po ibang mechanical test, hindi po natin magagawa. So, at least man lang po sa video, we are able to see how it is conducted and what are then the requirements para makonduct yung mga test po na iyon. Okay? So we start first po with mechanical testing in general, and then we go to the destructive testing, at ang huli po would be the non-destructive test. So, samples lang po yung ipapakita natin po dito. Okay? And then, bear with me kasi putol-putol po iyon. This is taken from YouTube. So, I need to play po each one. Okay? Kaya, ano na lang po. Paki-watch na lang po. And then, I'll have this po na naka-full screen. So, hindi ko po makikita yung message nyo kung dito sa meeting po natin kayo magme-message. Okay? So, kung may question po, may query po, you may send it po sa GC po natin sa Messenger. Okay? Halimbawa po, walang audio or kung ano mag-question nyo po, doon po sa Messenger nyo po, i-ano yung question po natin. I-post yung question natin. Okay? So, i-play ko lang po yung video ng sunod-sunod. Okay? Para makita ninyo po yung paano ba kinoconduct yung mga test na iyon. Okay? May question po ba?
Okay, so ito ang absolute extreme.
Wala naman po, ma'am.
Okay, so I'll play it now po. Sige pa.
Ayan. So ang sunod na
from the Stone Age to the Bronze Age, and from the Bronze Age to the Iron Age. The importance of materials has been recognized throughout history. One important attribute of materials is their strength characteristics, and through time, there have been many different tools for measuring the strength of materials. The oldest is the common hardness test, dating back to 1722. Hardness testing involves pushing a hard indenter into a sample with a known force and measuring the size of the residual indent. Different types of hardness test differ only in the shape and size of the indenter. For a given indenter and force, the indent size depends on the resistance of the sample to plastic deformation. A hardness number is defined as the force divided by the area of contact between indenter and specimen. At around 1890, late in the 19th century, early tensile test machines started to become available. The tensile test has remained since then the gold standard in mechanical testing, and it continues to be the go-to method for measuring stress-strain curves. During the test, a test coupon with a well-defined geometry is gripped at both ends before it is stretched under the application of a measured axial force. The degree to which the test coupon elongates is also continuously monitored, and when the test finishes, the measured forces and displacements can be converted to stresses and strains, such that the stress-strain curve can be obtained and analyzed. However, tensile testing also suffers from some limitations, including high capital investment costs, coupon preparation difficulties, and clamping and slippage challenges. Also emerging at about the same time, 1901, was the Charpy impact test for measuring the fracture energy of materials. The test technique is popular because of its simplicity and the ease with which specimens can be prepared, and it continues to be used extensively. The test consists of striking a suitable specimen with a hammer on a pendulum arm, while the specimen is held securely at each end. The hammer strikes the face that is opposite the face with the notch. The energy absorbed by the specimen is determined precisely by measuring the decrease in kinetic energy of the pendulum arm. But like time itself, technologies move on and new capabilities emerge. Indentation plastometry is a new method for measuring stress-strain curves and metal strength parameters. But it is simpler and quicker than conventional tensile testing, and you can test real components. Indentation plastometry involves the creation of an indent, followed by measurement of the full profile shape. This shape is then analyzed using finite element analyses and optimization algorithms in order to determine what the underlying strength characteristics of the material are. It can measure stress-strain curves in under 3 minutes. So, don't get left behind. Whatever your materials testing requirements are, it's probably best to make sure that you're no longer consigned to working in the Stone Age.
Wait lang po ha. Medyo humina yung connection. Loading pa.
So, ngayon, ang atin
The tensile test. First test, material with yield point phenomenon. In the first tensile test, a plain carbon steel with yield point phenomenon is to be tested. This is the test piece. It has a cylindrical test region with an original diameter of 10 millimeters and an original gauge length of 100 millimeters. Within this test region, distance marks have been drawn at regular intervals. They help to visualize and measure the plastic behavior of the specimen. Using a hand control, the tester moves the upper crosshead into its correct starting position. Now he can place the threaded ends of the test piece in the lower and upper grips of the testing machine. In the next step, he swings the extensometer into its working position and checks that everything is correctly prepared. Then he selects all necessary testing parameters on the control computer. Ready. The test starts and the extensometer's sensor arms are carefully pressed onto the test piece. This way, the gauge length can be measured throughout the whole tensile test. The gauge length is displayed at the bottom right-hand corner of the screen. At the beginning, it amounts to 100 millimeters. During the tensile test, the test piece is slowly and constantly elongated with a standardized speed. The force that the test piece opposes to the imposed elongation is recorded and can be seen at the bottom left-hand force elongation diagram. The force F is being plotted upwards on the vertical axis, the elongation delta L towards the right on the horizontal axis. At first, the force rises rapidly. Force and elongation are proportional and form a steep, straight line in the diagram. In this area, the material behaves elastically. If the test piece were to be unloaded from this area, it would spring back completely to its original length. In materials with yield point phenomenon, the end of the elastic area can be seen clearly. The plastic deformation starts abruptly and is accompanied by a sudden drop of force. If the test piece were to be unloaded now, it would not spring back to the original length, but instead show a permanent elongation. In the next stage of the tensile test, an almost constant force level with slight fluctuations occurs. This phenomenon is called the Luders effect. After a certain strain, known as the Luders strain, the force increases again. The material opposes an increasing force against the imposed elongation. It strain hardens. Up to the point of maximum force, the test piece is strained uniformly along its length. This means that the test piece gets longer and thinner but keeps a cylindrical shape. As soon as the maximum force is reached, a neck begins to form at one point of the test piece. All further plastic deformation now only takes place at the neck, and eventually the test piece fractures there. In the recorded force elongation diagram, the force FEH at the upper yield point can clearly be seen. This is the highest force the test piece can sustain elastically. FEL is defined as the force at the lower yield point, Fmax as the maximum force. Using these forces, the strength properties of materials can be calculated. The upper yield strength REH is calculated by dividing the force FEH by the original cross-sectional area S0. The lower yield strength REL is defined in a similar way. The maximum force divided by the original cross-sectional area is called tensile strength Rm. In the last step, the tester swings the extensometer back into its resting position and removes the broken test piece. On the work table, he puts the fragments back together again. With the help of the distance marks, the percentage elongation after fracture can be determined. This is the permanent strain after fracture and amounts to about 30% in this example. Please note that the percentage elongation after fracture depends on the length to diameter ratio. By measuring the smallest diameter at the point of fracture, the percentage reduction of area can be calculated. It describes the reduction of cross-sectional area at the point of fracture in relation to the original cross-sectional area. In the second tensile test, a material without yield point phenomenon is to be tested. In this case, it is a precipitation-strengthened aluminium alloy. The test piece has exactly the same shape and dimensions as the specimen in the first test. It is cylindrical, with an original diameter of 10 mm and an original gauge length of 100 mm. After fitting the test piece into the testing machine and panning the extensometer into its working position, the test can start. The initial linear curve in the force elongation diagram again shows the elastic behavior of the material. But this time, the end of the elastic area is not revealed by a sudden drop of force or any distinct change. There is a smooth and gradual transition from linear elastic behavior to plastic deformation. In the further course of the tensile test, the force increases and the test piece again is strained uniformly along its length. At the point of maximum force, a neck develops, and all subsequent plastic deformation is confined to this neck until fracture finally occurs there. As a common substitute for the yield strength, the 0.2% proof strength is used. It is the stress that causes 0.2% of plastic deformation in the material. And this is the way to calculate it. First of all, the elongation that corresponds to 0.2% of strain has to be computed. For an initial gauge length of 100 mm, the result is 0.2 mm. In the force elongation diagram, a straight line parallel to the elastic line is drawn through the offset point of 0.2 mm of elongation. The force at the intersection point of the offset line with the force elongation diagram is designated as Fp 0.2. This is the force that causes a plastic strain of 0.2%. The 0.2% proof strength, Rp 0.2, is equal to Fp 0.2 divided by the original cross-sectional area S0. Tensile strength, percentage elongation after fracture, and percentage reduction of area are calculated in the same way as in the first test.
We're using way too many platforms for work. We should just use Monday.com.
We're not using that many.
HRC.
The Charpy Impact Test. The standardized Charpy Impact Test has been designed to measure the toughness of materials under impact loading and multi-axial stress state. A pendulum impact testing machine is used to do so. The pendulum on the machine has a heavy weight at the end. This is lifted into the starting position in step 1. Then the tester checks whether the testing machine has been adjusted accurately. In order to do this, he turns the drag indicator downwards and releases the pendulum without a test specimen. The drag indicator stops at position 0. This proves that the pendulum has the correct starting position and that the friction is correctly compensated. The machine is ready for the tests. First test, strain-aged plain carbon steel S235. This is our test specimen. It has been machined to standardized size and shape with the characteristic V-shaped notch. The tester places the specimen on a support in the lower part of the machine and adjusts its position with a centering device. Next, he turns the drag indicator downwards again and checks that everything is prepared correctly. Perfect. The test can begin. The pendulum is released, it swings downwards and hits the specimen with its rounded hammer peen. The specimen absorbs part of the pendulum's energy, so the pendulum doesn't reach the full height on the other side. The amount of energy that has been absorbed by the specimen can now be read off at the position of the drag indicator. It only amounts to 13 joules in this test. Here is the main principle of the measurement. In its starting position, the pendulum only has potential energy. It is given by mass of the hammer m times gravitational acceleration g times starting height capital H. After the pendulum has been released, the hammer moves downwards, hits the specimen and then only swings to height small h. Exactly at the first reversal point, the pendulum again only has potential energy, which is m times g times small h. The energy that has been absorbed by the specimen is called notch impact energy, kV. It corresponds to the difference between the two potential energies. The first specimen only shows very little plastic deformation. A mostly flat, slightly glittering fracture surface has been formed. This is another important indication that this kind of steel is only able to absorb small amounts of notch impact energy. It shows mainly brittle behavior due to the strain aging effect. Second test. The second specimen has been made from normalized steel S235. It is also placed on the support and centered. The tester turns the drag indicator to its starting position, rechecks all safety measures and releases the pendulum. This time the impact sounds much deeper and richer. An impressive energy of 182 joules has been absorbed by the specimen. Here the specimen did not break into two pieces. Instead it was pushed through the counter bearings under heavy plastic deformation. In comparison with the strain-aged steel, the normalized steel absorbs much more notch impact energy and behaves in a very tough manner. The Charpy impact test is not only carried out at room temperature. Materials with body-centered cubic crystal structure, such as plain carbon steels, show a characteristic S-shaped curve of the impact energy versus temperature. In the so-called upper shelf region, the material absorbs a lot of energy and behaves in a tough manner. At low temperatures, in the lower shelf region, only a small amount of impact energy is absorbed and brittle fractures occur. Metallic materials with the face-centered cubic crystal structure, on the other hand, do not experience a ductile to brittle transition. These materials retain their ductile behavior towards low temperatures and are therefore well suited for low temperature applications.
If you're like me and you really want to be efficient when it comes to writing and editing your papers, I definitely recommend that you
The Brinell hardness test. Using the Brinell method, the hardness of a turbocharger housing is to be measured. First of all, the tester has to make himself familiar with the testing machine. A monitor and the control panel are positioned in the upper part of the machine. These are used to select and program different testing methods. Below the control panel, a microscope lens with a digital camera and an indenter are installed. These two elements are connected to each other and rotate towards the test piece as required. It is also possible to select and exchange the indenter, so different methods of hardness testing can be conducted on the same testing machine. The support table can be adjusted in height, so the test piece can be positioned at the correct distance to the microscope lens and the indenter. After becoming familiar with the machine, let's start the experiment. The principle of the Brinell hardness test is to press a hard spherical indenter with an exactly defined force onto the test piece, then evaluate the surface area of the indentation. The tester selects a suitable spherical indenter and inserts it into the holding device of the testing machine. Next, he puts the turbocharger housing onto the support table, rotates the microscope lens into vertical position and adjusts the correct height of the test piece. After bringing the test piece surface into focus, he selects the exact spot where the hardness test is to be made. By pushing the start button, the hardness test procedure begins. The testing machine rotates the lens back to its resting position and places the spherical indenter carefully on the test piece surface. Gradually and shock-free, the test force rises to its specified value. After maintaining the test force for a certain time, the indenter automatically lifts off again and the microscope lens pans back to its former position. The indentation can now clearly be seen on the monitor. With the control knob, the tester places 4 measuring lines on the edges of the indentation to measure its diameter. That's it. The testing machine can now calculate the Brinell hardness. The hardness value is defined as test force F in the old unit kilopond divided by the area of the indentation A in square millimeters. The result is displayed on the bottom left-hand corner of the screen and amounts to 250. The Rockwell hardness test, scale C. In this video, we will show how the Rockwell hardness test works using a gear wheel. The basic idea of this test method is to measure the permanent depth of indentation of a hard indenter under a test force. In the process variant scale C, a rounded cone made of diamond is used as an indenter. In step 1, the diamond cone is pressed onto the test piece surface with a minor force of 10 kilopons. The depth of indentation under this preliminary load is the reference point. In step 2, the test force is increased by 140 kilopons, which is acting as the major force. This means that an overall force of 150 kilopons is now acting on the indenter, and this force is held for a certain time. In step 3, the major force is removed again. While the minor force is still acting, the permanent increase in depth of indentation E is measured. This is how the Rockwell hardness is calculated. Rockwell hardness HRC is equal to 0.2 minus permanent depth of indentation E in millimeters times 500. Let's take a look at how the test is carried out in practice. The tester selects the conical diamond indenter and installs it in the testing machine. Then he picks up the gear wheel and puts it on the support table. After rotating the microscope lens to its vertical position, he can adjust his test piece. As soon as a focused image can be seen on the screen, the surface of the test piece is in the correct height. The test can start. In modern testing machines, the Rockwell hardness test is fully automated. That's why the Rockwell hardness test is used so often in automated production lines. That's it. The Rockwell hardness of our gear wheel is 55 HRC. This result is displayed on the screen. The Vickers hardness test. The hardness of a compressor wheel for a turbocharger is to be measured using the Vickers method. The main principle of this hardness testing method is to press a pyramid-shaped diamond indenter with an exactly defined force onto the test piece and then to evaluate the surface area of the indentation. First, the tester has to prepare his testing machine. He takes the Vickers indenter with the four-sided pyramid and inserts it into the mounting device of the testing machine. He then places the compressor wheel on the support table and rotates the microscope lens into its working position. With a hand wheel, he adjusts the height of the support table until the test piece surface is displayed in focus on the screen. Next, he moves the test piece around on the support table until the right spot for the hardness test is displayed. Now that everything has been prepared, let's begin with the test. After pushing the start button, the diamond pyramid pans down and carefully touches the test piece surface. The test force slowly increases to its specified value. After holding the test force constant for a certain time, the indenter lifts again, pans back, and the microscope lens resumes its former position. This is the magnified indentation on the display screen. With the control knob, the tester now places 4 measuring lines at the corners of the indentation. Doing that, he can easily measure the length of the 2 diagonals. Finally, he only has to push the input key. The Vickers hardness value will then be calculated automatically. It is equal to the test force F in the old unit kilopond divided by the area of the indentation A in square millimeters. The Vickers hardness of a compressor wheel is displayed on the bottom left-hand corner of the screen and amounts to 125.
Miss Janella, na-play ko yung Rockwell.
Yes po, ma'am. Tapos na po kami.
So, we're done with the destructive test. Okay, so next videos naman po are for the NDT.
Sa washing machine, kahit 2 sachet ng powder,
May tirang mancha? May powder pa.
Ay,
powder?
mag-Ariel Power Gel. Tunaw agad at may better stain removal na walang tirang powder. Basta washing machine, Ariel Power Gel!
Dye penetrant examination is an important method of non-destructive testing of materials. This is the basic principle. Often the surface of a workpiece is covered with rust or paint, which masks the material defects, as shown in the sectional view. Therefore, the first step is always the pre-cleaning of the test piece surfaces a crack are open to the surface. In the second step, the penetrant is applied to the test piece, usually red-colored low-viscosity oil. Due to the penetrant's high surface wetting capability, it penetrates into the defects and cracks. After several minutes of dwell time, the third step is to rinse the part's surface cautiously with water. The water removes the penetrant completely from the surface, but leaves it in the crack. Now, the fourth step. After drying the test piece, a developer is applied onto the surface. The developer is a fine-grained white powder suspended in a liquid. It forms an even coating on the surface. After drying, it draws penetrant from the crack out onto the surface. The location of the crack is indicated clearly on the surface. And this is how it is carried out in practice. We wish to inspect two samples, a segment of a worm gear shaft and a broken bicycle crank arm. Both test pieces have already been cleaned. First in line is the worm gear shaft. The material tester applies the penetrant. After a dwell time of about 10 minutes, she removes the excess penetrant from the surface by rinsing the test piece gently with water. She takes care not to rinse for an unnecessary long time because the penetrant is supposed to stay in the defects. Now she dries the surface of the sample with a cloth to absorb the excess water. As the final step, she applies the developer and lets it dry. That's it. Several cracks are indicated on the surface in deep red color. Next, the broken bicycle crank arm has to undergo the dye penetration test. Spraying with penetrant, allowing to soak, rinsing, drying, and applying developer. Clearly, additional cracks are indicated on the fragments. Finally, the pros and cons at a glance. Advantages of this test method are: almost all materials can be tested, and the method is simple and low cost for a single inspection. Disadvantages are: only suitable for surface defects. No information about the depth of flaws can be gained, and rough surfaces are difficult to test. Non-destructive testing. Magnetic particle inspection. The magnetic particle examination is an excellent method to investigate near-surface defects in ferromagnetic materials. This video shows the basic principle and the practical procedure. The material tester gets the machine ready for use and inserts the test piece between the two poles of an electromagnet. Then she takes a bottle with a suspension of magnetic particles, turns on the electromagnet with a foot switch, and applies the suspension of magnetic particles onto the test piece. Already in daylight, dark lines are visible on the surface. The lines can be seen much better under ultraviolet light, and particularly well at darkening the daylight. The suspension contains pigments that cover the magnetic particles and fluoresce under ultraviolet light. The particles run off in areas free from defects, and they are attracted and clustered near defects. This workpiece shows a whole array of cracks. The basic principle is to magnetize a ferromagnetic workpiece parallel to its surface, as shown in the sectional view. If the workpiece is free from defects, the magnetic field lines run within the workpiece and parallel to its surface. In places of magnetic inhomogeneity, for instance near cracks, the magnetic field lines will locally leave the surface and a leakage field occurs. Now, if a suspension of ferromagnetic particles is applied onto the test piece surface, the magnetic particles will run off at defect-free areas. In places of leakage fields, the magnetic particles are attracted and clustered together, thus indicating the place of the defect. The method works best using a pigment which covers the magnetic particles and shows fluorescence under ultraviolet light. Even cracks can be detected that are not open to the surface but just below it, as long as they are not too far below the surface. But one precondition must always be fulfilled. The magnetic field lines must be perpendicular, or at least at a certain angle to the defect. Otherwise there will be no leakage field and the defects remain undetected. Our test sample has been magnetized in horizontal direction. The magnetic field lines run horizontally. This is the reason why cracks in vertical direction are visible particularly well. To make sure to detect all near-surface cracks, one has to magnetize the sample once more and best perpendicularly to the first time. To do this, the material tester switches the machine over to the current flow method. A high electric current flows through the sample, generating a circular magnetic field. Now the cracks in horizontal direction can be seen very well. The tested sample is a hardened sliding guide. The cracks have been formed during the hardening process and the subsequent grinding operation. Still, another test piece has to face the magnetic particle inspection, a section of a large gear wheel. The same procedure again. Placing the gear wheel between the magnetic pole pieces, magnetizing and applying magnetic particle suspension. Already in daylight, there are indications of cracks, and again, they are best visible under ultraviolet light while darkening the daylight. The visible cracks are so-called fatigue cracks. They have been generated during the operation of the gear drive due to a mismatch of the gear wheels. Non-destructive testing. Ultrasonic examination. The basic principle of ultrasonic testing of materials is the propagation and reflection of sound waves. As an example, a cylindrical workpiece is shown in the animation. The longitudinal section through the cylinder shows the position of the atoms extremely magnified and simplified as a single crystal. To begin with, a rigid unyielding stop is attached to the right front end of the cylinder. At the left front end, a disc is installed. It will be used to transmit and receive sound waves. Pushing and pulling briefly at the disc causes a longitudinal sound wave to propagate through the cylinder. When the sound wave reaches the rigid stop at the right side, it is reflected and runs back towards the disc, which now serves as a receiver. A free end is also able to reflect a wave. In this case, however, the tensile side runs ahead in the reflected wave and finally deflects the receiver to the right. The reflected wave is even reflected again and actually travels for several times across the length of the cylinder, but this is not shown in the animation for the sake of simplicity. So, if a sound wave is generated at one end of a workpiece, it will travel through the material with its speed of sound. At the free end of the workpiece, the sound wave is reflected and it returns to the transmitter, which then acts as a receiver. For ultrasonic testing of a workpiece, not a large transmitter is used in most cases, but a rather compact one, which generates a short ultrasonic pulse. At a place free from defects, the ultrasonic pulse travels to the right front end, also termed backwall. The pulse is reflected and recorded again as an echo. When the transmitter is moved a little downwards, the cavity reflects a part of the wave. That part arrives earlier at the transmitter than the rest of the sound wave. Even further downwards, the cavity reflects the complete ultrasonic pulse. For material testing, either the echo of a defect can be utilized, this is the pulse echo mode, or the phenomenon that hardly any sound waves pass through the imperfection. This is called the through transmission mode. In pulse echo mode, a transducer installed in a probe performs both the sending and the receiving of the ultrasonic pulse. On a computer monitor, the intensity is being plotted upwards on the y-axis and the time towards the right on the x-axis. With the probe at a place free from defects, only two signals may be seen on the monitor: the transmission pulse and the echo resulting from the lower surface of the workpiece, termed back wall echo. Moving the probe towards the right leads to an additional echo created by the defect. Even further towards the right, only the defect echo is visible apart from the transmission pulse. In our laboratory, there's a green painted steel cylinder to be found. It contains artificial defects which are invisible from the outside. To track down the defects, the material tester uses the pulse echo method. This is how a typical probe looks like. Under the bright wear plate, a piezoelectric disc is installed. It can transmit and receive ultrasonic pulses. A computer operates the probe via a plug-in card and power electronics. On the monitor, the intensity is plotted upwards and the time is plotted to the right. After placing the probe on top of the cylinder, initially no echo at all may be seen on the monitor. The reason for this is the too small contact area between the probe and the workpiece. Only with the use of a gel, the so-called couplant, the ultrasonic pulses can get into the workpiece and can also go back into the probe. Now the back wall echo turns up on the monitor. The material tester spreads out the gel evenly on the top surface. That way she is able to examine the entire cylinder. Using the velocity of sound in the material, one can plot the calculated depth on the monitor to the right instead of time. A very useful feature. With the help of so-called trigger gates, which may be set on the echoes with a computer mouse, the depth of the defects can easily be read off at the lower left-hand corner of the monitor. The cylinder back wall lies in a depth of about 200 millimeters below the probe, so the cylinder has a height of 200 millimeters. And here we go. The material tester scans the upper front end of the cylinder with a probe and observes the monitor. A defect echo appears on the monitor. This defect is located in a depth of 130 millimeters below the surface. Another echo indicates a defect in a depth of 87 millimeters. The second smaller echo at 174 millimeters is caused by double reflection on the same imperfection. And these are the defects: a drill hole and a saw cut. Filled up near the surface and painted, they are not visible from the outside. The drill hole in a depth of 130 millimeters. The saw cut 87 millimeters below the surface. Trams are popular means of transport in Karlsruhe in southern Germany. The tram cars are not only cleaned regularly, but also tested thoroughly in regular intervals by the transport company. Among many other maintenance points, the ultrasonic examination of the wheel axles plays an important role. A tram enters the maintenance hall for inspection. Some of the tram cars have already been lifted up. That way the bogies can easily be detached, pushed forward and examined carefully. This is one of the bogies, jacked up to comfortable working height and prepared for ultrasonic inspection. Special attention is given to the wheel axle, among experts known as wheel set axle. It has been designed as a hollow axle. This saves weight and facilitates the ultrasonic examination. The material tester applies a suitable oil as a couplant into the bore of the axle. Now he takes a special probe designed exactly for this purpose inserts it carefully into the bore with a mount, and evenly spreads out the couplant by turning and pushing. He has accurately marked the most important examination points at the mount. In an experienced manner, he positions the probe at the appropriate places within the wheel set axle and watches the monitor closely. The probe has specially been designed for this application. It transmits the ultrasonic pulses at an angle of 45 degrees. At a place without defects, no defect echo returns. But when the pulse encounters a crack which has grown in from the outside, double reflection occurs and a typical defect echo is recorded. It is important to note that also the shape of the wheel set axle may lead to an echo, for example at shoulders. These are so-called contour echoes. In this particular case, only contour echoes are recorded. No abnormality has been detected. The wheel set axle is perfect and can be used again to transport many passengers until the next examination becomes due.
Need to turn this into this? Try Lucid Chart. Intelligent diagramming where you don't just tell.
Non-destructive examination, eddy current testing. Eddy current testing has been indispensable for a long time, both as a non-destructive material examination by hand and as a fully automatic method. Near-surface defects in workpieces can be tracked and specific material properties can be determined. How does eddy current testing work? It is based on electromagnetic induction. The animation shows a coil, which can be connected via an electric current meter to a voltage source. After applying a direct voltage to the coil, the electric current first increases fairly quickly, then more slowly, according to the inductance of the coil. Eventually, it reaches a level resulting only from the ohmic resistance of the coil. The current creates magnetic fields that flow around every small piece of coil winding. The individual fields superimpose and form the total magnetic field depicted here in blue. If an alternating voltage is applied to the coil, the effective current through the coil is much smaller than when applying direct voltage. The reason for this is the alternating magnetic field, which generates a countervoltage in the coil by self-induction. The countervoltage in turn reduces the current consumption. Pushing an electrically conductive tube through the coil increases the effective current significantly. This is because the alternating magnetic field of the coil induces a current in the tube in circumferential direction, the eddy current. The eddy current in turn generates its own magnetic field, which counteracts the magnetic field of the coil. Consequently, the self-induction is low and the current consumption high. When a defect, for example a crack, comes into the path of the eddy current, the current consumption of the coil drops. The eddy current has to flow around the defect. The path of the eddy current is now longer, and the electrical resistance of the eddy current circuit is larger. This leads to a reduced magnitude and a reduced magnetic field of the eddy current. The self-inductance of the coil is increased, and the current consumption decreased. In practice, the alternating current frequencies are not as low as shown here for demonstration. They are much higher, typically in the region of some kilohertz. From now on, we're going to omit the magnetic field lines in the animation and represent the eddy current in a simplified static way. How does the technique work in practice? In eddy current testing with coaxial probes, the coils are either pushed coaxially over the workpiece or pushed through the workpiece. This is our simple test setup: the alternating voltage source, the electric current meter, the coil. Cables lead from the alternating voltage source to the electric current meter, then to the coil, and back again to the voltage source. Our sample is a tube made from an austenitic non-magnetic steel. We have purposely machined 2 cuts through the tube wall, one in longitudinal direction and one in circumferential direction. And here we go. The materials tester connects the return cable to the alternating voltage source. This closes the electrical circuit. The current consumption of the coil is still relatively low. Once the coil is positioned over the intact part of the tube, the magnitude of the current is high. The current decreases in the region of the longitudinal cut and reaches the original magnitude again in the intact part of the tube. The cut in circumferential direction has apparently no influence on the current. The animation shows the physical background. Low current consumption as long as the coil is still far away from the tube. The reason for this is the undisturbed self-induction. Much higher current in a region where the tube is intact. The reason here is the eddy current, its own magnetic field, and the reduced inductance of the coil. Smaller current consumption at the longitudinal cut because the path of the eddy current is longer. The eddy current is lower and its magnetic field is smaller here. Full current consumption at the region with the saw cut in circumferential direction, as if there were no cut at all. The flow of the eddy current is almost undisturbed. Obviously, it is not possible to detect crack-like defects that run along the flow lines of the eddy current. Back in the laboratory, we observe the same phenomenon in reverse direction. This technique can be improved considerably if not only a single coil, but several coils are used. The original coil, which is now called the excitation coil, is supplemented with the receiver coil on the left side, and a receiver coil on the right side. A voltage meter is connected to each of the receiver coils. The improved test arrangement has been set up in the laboratory and is now in operation, as can be seen from the current consumption of the excitation coil. First, the materials tester picks up the right receiver coil and places it over the tube. The excitation coil is next in turn. As soon as he pushes it over the tube, the current consumption increases, exactly as in the previous test. Last in turn is the left receiver coil. He carefully takes all 3 coils and moves them to the right. The pointer of the right voltage meter deflects, then the pointer of the left voltage meter. Further to the right, where the tube is intact, the pointers of none of the voltage meters are deflected. Unfortunately, the saw cut in circumferential direction is again not detectable. The animation once more shows the physical background. The current consumption is high in an area where the tube is intact. The reason for this is the undisturbed flow of the eddy current. Because the magnetic field of the eddy current doesn't flow through any of the 2 receiver coils, we measure virtually no voltage on them. As soon as the excitation coil reaches the left end of the longitudinal saw cut, the current consumption decreases. The reason for this is the longer path of the eddy current. Because the eddy current now flows partly underneath the right receiver coil, its alternating magnetic field induces a voltage there. When the excitation coil reaches the right end of the longitudinal saw cut, the eddy current partially flows under the left receiver coil and induces a voltage there. Still further to the right, near the saw cut in circumferential direction, the eddy current is undisturbed. Its alternating magnetic field flows neither through the left nor the right receiver coil. The voltage meters indicate almost nothing. Back in the laboratory, we observe the same phenomena in reverse direction of movement. First, the pointer of the left voltage meter deflects, then the pointer of the right voltage meter. Still only one voltage meter, which is connected. The technique connected to the right-hand terminals of the receiver coils, and if the left terminals of the receiver coils are connected to each other. The voltage meter now indicates the difference of the voltages induced in the 2 receiver coils. We have set up this test arrangement in the laboratory too. The voltage meter clearly indicates the ends of the longitudinal saw cut. Unfortunately, even this arrangement cannot detect the saw cut in circumferential direction. If the coils are optimized even further, much smaller defects than our large saw cuts can be detected. This tube is made of a non-magnetic austenitic steel. 4 bore holes have been drilled through the tube, starting with a diameter of 1.4 mm and ending with 0.8 mm. Now, instead of performing the test by hand, we prefer to use a mechanized testing machine. The tube is firmly fixed in the testing machine on the right and the left side. After pushing the start button, the machine carriage moves several coaxial coils along the tube with the bore holes. By choosing appropriate test parameters and an optimized evaluation method, not only the locations of the holes along the axis may be determined. The diameter of the holes can also be measured approximately, a really neat feature. But one thing cannot be determined with this coaxial probe. It is the location of the defects in circumferential direction. Here we need another version, the eddy current testing with surface probes. We want to show this version in our laboratory too. Here the test piece is not a tube, but a sheet, again made of an austenitic steel. It has a saw cut in the middle, going right through the sheet. In contrast to the coaxial probes, the coil is not pushed over a tube, but instead placed with its flat side on the surface of the test piece. In defect-free areas, the current consumption of the coil is high. In the area of the saw cut, the current drops noticeably and reaches its full height again in the intact area. The same effect can be observed when the coil is moved across the saw cut from top to bottom. The animation shows that the current consumption is low when the coil is still far away from the sheet. This is due to high self-induction. As soon as the coil is placed on the sheet surface, the current increases. Once more, the reason is an eddy current that flows in the sheet in close vicinity of the coil. The eddy current again creates its own alternating magnetic field which counteracts the magnetic field of the coil and reduces the inductance. When the coil is located over the saw cut, the current consumption drops. The eddy current can no longer flow freely and must take a detour around the saw cut. This in turn decreases the strength of the eddy current. The magnetic field of the eddy current is weaker and interacts less with the coil. In the intact part of the sheet, the eddy current flows unrestrictedly again, and the current consumption of the coil is high. Eddy current testing with surface probes can also be refined by using not just one coil, but 3. The middle coil is the excitation coil. The 2 outer ones are the receiver coils. When all 3 coils are moved over the sheet surface, the pointer of the right voltmeter deflects first, then the pointer of the left voltmeter. And this is the reason. The current consumption of the excitation coil is high in an intact area of the sheet, where the eddy current flows freely. Because the eddy current path is slightly larger in diameter than the excitation coil, the magnetic field of the eddy current partially flows through the left receiver coil and already now induces a small voltage in it. In the same manner, a small voltage is induced in the right receiver coil. As expected, the current consumption is lower when the excitation coil is positioned on the left side of the saw cut. Now the magnetic field flowing through the right receiver coil is much stronger than before. Therefore, the induced voltage here is high. The situation is equivalent when the excitation coil is on the right side of the saw cut. The magnetic field of the eddy current now flows through the left receiver coil more intensely. The voltage induced there is correspondingly high. Although the technique with the arrangement of adjacent coils seems impressive, it has disadvantages. The local resolution is not particularly good, and very small defects are difficult to detect. We can achieve a substantial improvement with this layout of coils. The excitation coil remains unchanged. The right receiver coil is wound in the form of a capital D and sits within the excitation coil. The left receiver coil is laterally inverted. When testing this coil set in the laboratory, we are initially disappointed. Firstly, already in the intact region of the sheet, a high voltage is induced in the receiver coils. This is because the receiver coils are now positioned within the excitation coil. Secondly, the saw cut is only faintly detectable. Now we use a trick that we have already applied to the coaxial probes. We switch the receiver coils against each other and only measure the voltage difference between them. Now everything works in a way that suits us. Small voltage difference in the intact sheet, strong voltage fluctuations at the left side of the saw cut, and at the right side. But one point should always be kept in mind. The two D-shaped receiver coils must have the correct orientation for saw cuts and cracks. Otherwise you measure only little or nothing at all. If the orientation of cracks is not known, the probe is rotated by 90 degrees after the first pass and the test piece is scanned a second time. To demonstrate the basic principle, we have chosen rather large coils so far. However, the disadvantage of large coils is that only large defects, such as our rough saw cuts, can be detected. In practice, mostly very small coils are used, as shown in the example on the left-hand side. In this way, also small defects can be detected. The coils don't have to be round or D-shaped, but can also have a rectangular cross-section. Now let's take a look at the examination of a component in practice. As an example, we are going to inspect a bicycle crank arm with a crack. To do so, the materials tester uses a suitable eddy current probe. It has a tiny sensor with an excitation coil and two inner receiver coils on its tip. He carefully scans the surface of the bicycle crank arm with the probe. The monitor of the testing equipment shows almost no signal at an intact spot. But as soon as the probe scans over the crack in the crank arm, strong signals are visible. The right half of the monitor shows the complex impedance plane with the imaginary and real parts of the sensor signals. This version of eddy current testing is also well suited for mechanization. 3 very fine saw cuts with varying depths have been machined into this massive cylindrical rod in longitudinal direction. The rod is again made of an austenitic steel. The materials tester pushes the test piece with constant speed into the machine, so that the saw cuts pass through the actual test area. A look into the interior of the machine shows the rod in the center. Here, the rod is not only scanned by just one probe, but in fact by 4. And each of the probes is equipped not only with a single coil, but with several ones. The probes are positioned radially at a small distance from the rod surface. During operation, they rotate around the rod at high speed. Meanwhile, the rod moves through the machine in longitudinal direction. Here, several frequencies are used for testing. Thereby, the penetration depth of the eddy currents can be varied. This helps to determine not only the location of the defects, but also their approximate depth. And this is where eddy current testing really starts.
This lecture is on
Okay, so we have presented there the videos for the different mechanical tests, okay? So particularly for the destructive testing, we come up with the tensile test, we have yung Charpy, okay? And the different hardness test, okay? Such as the Brinell, Rockwell, and yung Vickers, okay? I hope you had seen the differences doon sa tatlong hardness testing techniques po natin, okay? The way, the use of the indenters, okay? And also the computation on the hardness number, okay? So, it is clearly stated po doon sa video, okay? So, kaya nga po sabi ko sa inyo last time that we cannot compare the hardness of the material kung iba-iba pong scale yung ginagamit, okay? We can compare only hardness values kung pare-parehas po yung hardness testing technique na kinonduct po. Okay? And then for yun naman pong sa tensile test, pakitandaan lang po kasi that is very the same doon po sa i-conduct po natin on Thursday. And the Charpy naman po, okay? So, I'll just check if okay pa po yung machine dito, okay? At yun po ay i-conduct din po natin. Okay? And then on the NDT naman po, we have the liquid penetrant test, magnetic particle testing. Also, we have yung ultrasonic, which is, sabi ko nga po, that is very similar to ultrasound po na ginagawa sa katawan natin. And the last one is the eddy current testing. Okay? So, sana po you have a grasp of this different mechanical test na nandun po sa video. Okay? So, lalo na po yung hindi po natin mape-perform, at least nakita man lang po natin doon sa video how it is conducted. Okay? So, may question po ba sila? Hello?
Wala naman po.
Okay, wala. So, let us have, I'll end the meet na po. Pakibukas lang muna po ng ating camera para po sa atin na attendance. So yung again, wala po tayo magiging meeting tomorrow, but instead po doon na po sa experiment na po natin on Thursday. Okay? Okay, Miss Janela.
Okay po. 1, 2, 3.
Okay. Good.
Isa pa po. One, two, three.
Okay, thank
Wait
you.
lang po, isa pa po. Nag-close po sa akin ng mga camera po. Wait lang. Isa pa po. 1, 2, 3. Okay na po.
Okay na.
Thank you po.
Again, at another thing, Miss Janela, you have submitted to me all the class activities, yung classworks po natin. Okay? Kindly bring na lang yung expandable folder. So, if you have their color yellow, okay, or not green, blue, and red. Okay? Basta hindi yun. Para mailagay po yung inyong activities. Okay?
Okay po, ma'am. Dadalhin ko na lang po on Thursday.
Okay, okay. Thank you. So, I'll end the bit now.
Thank you
Bye po. See you on Thursday. Thank you.
Thank you po, ma'am.